So in this video, I want to talk about the Doppler equation and the Doppler effect. So imagine we have the speaker. We know the speaker can create sound. And the way it does that is it vibrates. And when it vibrates nearby air, and then this air travels, creating a sound wave. And this sound wave is going to have regions of compressed air and regions of non-compressed air. And the distance between two regions of compressed air determine the frequency of the sound. So if these two regions of compressed air are nearby each other, this sound wave will have a high frequency. However, if the distance between two regions of compressed air are far away from each other, this sound wave will have a low frequency. So let's imagine this speaker is creating a sound wave. What is going to be the velocity of this sound wave? Well, the velocity of sound is determined based on the temperature of the room and the medium in which the sound wave travels through. So what do I mean? So let's imagine two different rooms. Let's say this room has a temperature of 20 degrees Celsius. Well, under that temperature, this sound wave will travel at a velocity of 343 meters per second. However, if we have a different room that has a temperature of 35 degrees Celsius, then this sound wave will travel at 350 meters per second. So we can see how the temperature determines the velocity of sound. But also the medium determines the velocity of sound. For example, sound travels through air at a different velocity than it travels through a solid, or that it travels through a liquid. So these are the two variables that determine the velocity of sound. So for the rest of this video, let's imagine all these examples occur in a room that's 20 degrees Celsius, just so we can keep things consistent. So let's imagine we have a stationary speaker that's not moving. We know this speaker can create a sound wave, and this sound wave will travel at a certain velocity. And eventually this sound wave will reach this person that is acting as a detector. It's detecting the sound wave. Now let's imagine a speaker that's hooked onto this car that's traveling at 100 meters per second. So now we know the speaker is moving at 100 meters per second towards this detector. And now let's imagine this speaker creates a sound wave. We know the sound wave will travel with a certain velocity. And now let's imagine a speaker that's hooked onto a car that's traveling at 100 meters per second away from the detector. And now let's imagine the speaker creates a sound wave. We know this sound wave will travel with a certain velocity. So you might wonder, which of these sound waves are traveling at the highest velocity? Well, you may think this one because of that relative motion. We know if the speaker is moving at 100 meters per second and then creates a sound wave, it makes sense that this sound wave will travel 100 meters per second faster than the stationary speaker creating the sound wave. Well, in reality, that's not true. And in reality, all of these sound waves travel at the same velocity of 343 meters per second. Because we know the two variables that determine the velocity of sound is temperature and the medium in which the sound is traveling through. So there's no such thing as relative motion when it comes to the speed of sound. And it's just the nature of the way sound travels. We know this speaker is going to vibrate and it's going to vibrate the air nearby, and that sound wave is going to travel. However, this relative motion does not impact the velocity of the speed of sound. However, now let's imagine a different example. So let's say the speaker is stationary, so it has no velocity, it's not moving. And let's say the speaker creates a sound wave with the frequency of 1,000 hertz. So then it's going to create the sound wave with the frequency of 1,000 hertz, which tells us about the difference between these two regions of compressed air. So the sound wave will travel, and eventually this detector will detect the sound wave, and it's going to detect a frequency of 1,000 hertz, which makes sense. This speaker is creating sound at 1,000 hertz. That's the distance between these two regions of compressed air. So it makes sense that when this detector hears that sound, they're going to hear a sound at 1,000 hertz. And the way this works is as the sound travels by this detector is going to hear those regions of compressed air. So they're going to hear a certain frequency. But now let's imagine another example. Let's imagine this speaker is hooked onto this car. And let's say this car is traveling at 100 meters per second towards this detector. So let's say the speaker is programmed to create a frequency of 1,000 hertz. So we know this 1,000 hertz tells us about the distance between two regions of compressed air. However, because this car is traveling at 100 meters per second, what's going to happen? Well, we know it's going to vibrate, so it's going to create regions of compressed air. But once it creates this region of compressed air, it's going to travel. It's going to move at 100 meters per second. And then it's going to create another region of compressed air. And then it's going to travel at 100 meters per second. Then it's going to create another region of compressed air. So essentially what's happening is these regions of compressed air are being squished apart because this speaker is moving forward. So this speaker is catching up with these previous regions of compressed air. So that is essentially going to create sound with a higher frequency, with regions of compressed air that are closer together. So therefore, this detector will hear sound at a higher frequency. Because again, due to this motion, these regions of compressed air are going to get squished apart. But now let's imagine the opposite example, where this car is moving away from the detector. Well, again, it's going to create sound, and let's say this is also programmed to create sound at 1,000 hertz. So again, that tells us about the distance between two regions of compressed air. But because this is moving away from the detector, we know it's going to vibrate, and it's going to create regions of compressed air, but then it's going to move away. And as it moves away, then it'll create another region of compressed air. Now it's going to move away even further and create another region of compressed air. So these regions of compressed air are getting further and further apart due to this relative motion. So if these regions of air are getting further apart, this frequency is going to be a lower frequency. So this detector will hear sound at a lower frequency compared to the initial frequency that this speaker made. So what's the point? Well, the point is that the velocity of the speaker impacts the frequency that's heard by this detector. So again, when the speaker is not moving, the frequency it produces is the same frequency that the detector hears. However, if the velocity of the speaker, which is the source of sound, is moving towards the detector, then even though it produces sound at a frequency of 1,000 hertz per second, because it's moving and creating more regions of compressed air, squishing these regions of compressed air, the detector will hear sound at a higher frequency relative to the frequency that's produced by this car. And again, in the same thing in this example, because the velocity of the speaker is moving away from the detector, therefore, the frequency that's heard by the detector will be lower than the frequency that was produced by the speaker. So the point is the velocity of the speaker, or you can say the velocity of the source of sound, determines the frequency that's heard by the detector. So that's the first important point. And we can see that in this Doppler equation. We can see the velocity of the speaker, the velocity of the source of sound, has an impact on the frequency heard by the detector. So now let's imagine another example. Let's say we have this speaker that's not moving, it's stationary, so it has no velocity, and it's programmed to create sound at a frequency of 1,000 hertz. And now let's imagine this detector isn't moving, it has no velocity. So then it's going to hear this sound at a frequency of 1,000 hertz, which again makes sense. It's producing sound at 1,000 hertz, so this detector will hear sound at 1,000 hertz. But now let's imagine another example. So let's say everything is the same, it's the same conditions, except let's say this detector is moving towards the sound at a velocity of 100 meters per second. What's going to happen? Well, this speaker is creating sound with a frequency of 1,000 hertz. However, because this detector is moving towards the sound, It's going to run and then it's going to hear the sound. Then it's going to run and hear this sound. Then it's going to run and hear this sound. So this detector is going to perceive sound at a higher frequency. And that makes sense because, again, the speaker creates sound at 1,000 frequency hertz. However, because it's going to run through the sound, it's going to quickly hear all these regions of compressed air. So this guy is going to perceive sound at a higher frequency compared to the frequency that was actually produced by the source of sound. And another example, let's say the speaker creates sound again at 1,000 hertz, but now let's say this detector is running away from the sound. Well, it's essentially going to be the opposite scenario to this guy. Because remember, this guy's running towards the sound, so it's going to hear all these regions of compressed air within a quicker period of time. So this guy's going to perceive a higher frequency. However, in the opposite example, it's going to run away from these regions of compressed air, so it's going to hear sound at a lower frequency. Which makes sense because this region of compressed air is going to run by this guy. But what's going to happen? This guy's going to continue to run, so then it's going to take time for this region of compressed air to reach him. And this guy's going to still run, so it's going to take time for this region of compressed air. So this guy's going to hear these regions of compressed air at a lower frequency. So this guy's going to perceive sound at a lower frequency compared to the frequency that was produced by the speaker. So the point is, the frequency that's determined by this detector is impacted by the velocity of the detector. And again, we saw that when the detector is moving towards the sound, it hears a higher frequency. When the detector is moving away from the sound, it'll hear the sound at a lower frequency. So we can see the velocity of this detector will impact the frequency perceived by this detector. And again, we can also see that in this Doppler equation. We can see the velocity of the detector determines the frequency perceived by this detector. So now let's imagine one last example. So imagine the speaker stationary, and let's say this detector is stationary, but let's say the speaker creates sound at a frequency of 1,000 hertz. So it makes sense this detector will perceive sound at a frequency of 1,000 hertz. However, what if we have the exact same situation except the speaker is programmed to create sound at 2,000 hertz? Well, if they're both not moving, it makes sense that this detector will perceive sound at 2,000 hertz. Pretty straightforward. And the same thing if the speaker creates sound at 3,000 hertz. If they're both not moving, it makes sense that this detector will perceive sound at 3,000 hertz. So the last point is that the frequency that's produced by the source of sound also determines the frequency that's perceived by the detector. So now we know the variables that determine the frequency perceived by this detector. We know the velocity of the source of sound determines the frequency that's perceived by this detector. We also know the velocity of this detector determines the frequency perceived by the detector. And we also know the frequency produced by the source of sound determines the frequency perceived by this detector. And again, this is just review. This is exactly what we've just talked about before. But also the velocity of sound also determines the frequency perceived by this detector. So again, these are the variables that determine the frequency that is perceived by this detector. And that is what's going on in this Doppler equation. We see these are the variables that determine the frequency perceived. So that's what's going on. These are the variables that determine the frequency perceived by this detector. So let's do an example. Let's say the velocity of the source of sound, or you can say the velocity of the speaker, is 0 meters per second, so it's not moving. Let's say it's programmed to create sound at 25,000 hertz frequency. Let's say the velocity of sound is 343 meters per second. And let's say the velocity of this detector is 0 meters per second. So this detector is stationary, it's not moving. Under these conditions, what's going to be the frequency of sound perceived by this detector? Well, we know how to do this. We just simply use this Doppler equation. So it's pretty straightforward. You just plug in all the values. Again, the frequency of sound you would plug in here. The velocity of sound you would plug in here and here. So this 343 meters per second you would plug in twice. The velocity of this detector is 0 meters per second, so you would plug that in here. And the velocity of the source of sound is also 0 meters per second, so you would plug that in here. So if you did that, you would be left with this guy. So then you would just solve this. And notice here we have 343 meters per second plus or minus 0 meters per second. Well, it doesn't really matter if it's plus or minus because it's 0. It's 0 meters per second. So whether it's plus or minus, it doesn't really matter. So we don't really even need to worry about that for both these situations. So again, we just simply do the math and we would be left with the frequency of 25,000 hertz. So that's the frequency of sound perceived by this detector. So pretty straightforward. However, now let's do a difficult example. So let's say the velocity of this speaker is 0 meters per second. It's stationary. Let's say it's programmed to create sound at a frequency of 1,000 hertz. Let's say the velocity of the sound is 343 meters per second. But let's say the velocity of this detector, this guy detecting sound, is 100 meters per second running towards the sound. In this situation, what's going to be the frequency of sound perceived by this detector? Well, we just plug in all the values. Again, 1,000 hertz, we plug in here. 343 meters per second, we plug in both these values. We know 0 meters per second for the velocity of the source of sound. And we know 100 meters per second for the velocity of the detector, the guy detecting sound. So we plug in all those values and we're left with this. So again, we would just solve this. And again, because this is 0, whether this is plus or minus doesn't matter. Whether you plus 0 or minus 0, it's the same thing. So you can just ignore this. However, what about this guy? Here it does matter. Whether we add 100 or if we subtract 100, that will dramatically change the frequency perceived. So this is important. So we have to know, should this be plus or should this be minus? Well, you have to think about it and just use logic. So again, if this source of sound is creating sound at a frequency of 1,000 hertz, and if this detector is moving towards the sound, it makes sense that this detector will perceive a sound higher relative to the sound that's actually produced. Because again, this speaker creates sound at 1,000 hertz, so that tells us about the distance between two regions of compressed air. However, because this guy is running towards the sound with this velocity, it's going to quickly hear all these regions of compressed air. As it's running, it's going to hear this region, then quickly hear this region, then quickly hear this region. So this guy is going to perceive sound at a higher frequency relative to the sound that's actually produced. So therefore, we know this velocity of this detector should increase the frequency perceived. So how do we increase the frequency perceived when it's plus or minus? Well, let's try both examples. Let's imagine we plus this 100 meters per second, again, the velocity of this detector, and let's imagine we subtract this velocity of this detector. And let's solve the math. So when we add it, we essentially increase this numerator, which increases the frequency perceived. In this example, when it's minus, we decrease the numerator, which decreases the frequency perceived. And again, we know this guy should perceive a higher frequency relative to the frequency produced. So we know this frequency should be higher than the frequency produced. So we see that happens in this example when we add it. So now we know that's the way we have to go. So we ignore this and we know we have to add it. So you just have to use some common sense. When you're determining whether you use plus or minus, you just have to use common sense. So we know this guy should perceive sound at a higher frequency relative to the sound produced. So we know this is positive. So then we just solve the math and we get an answer. So now we know this guy will perceive sound at a frequency of 1,291.5 hertz. So now let's imagine a really tricky example. So let's say the speaker is programmed to create sound at a hertz of 300 hertz. And let's say the sound travels at a velocity of 343 meters per second. And let's say the velocity of this source of sound is moving towards the detector at a velocity of 200 meters per second. And let's say this detector is moving towards the source of sound at a velocity of 150 meters per second. What's going to be the frequency perceived by this detector? Well, again, we know we use the Doppler equation. So we simply plug in all the variables. So again, we plug in all these variables. Again, we plug this guy in here and we plug this guy in here. So we plug in all our values. However, now we have to wonder, is this plus or minus, and is this plus or minus? Because again, whether this is plus or minus and whether this is plus or minus will dramatically change this frequency value. So how do we determine this? Well, we just have to use some logic. So again, we already explained, because this guy's moving towards the sound, it's going to quickly hear all these regions of compressed air. So this guy's going to perceive a higher frequency relative to the frequency produced. So we know this velocity of the detector, this should raise the frequency. This should raise the frequency perceived. So how do we do that? Well, we know we have to add it. Because if this velocity of the detector increases the frequency perceived, then we know the way we do that is we add it. Because if we add, if this is positive, we increase the numerator, which will increase the value of this fraction, which will therefore increase the frequency and lead to an increase in frequency. So we know just using a little bit of logic, this has to be positive. So what about the velocity of the speaker? Well, again, we know it's moving towards the detector. So what's going to happen? Well, again, the speaker's going to vibrate and it's going to create regions of compressed air. And then it's going to move forward and then create another region of compressed air. And then it's going to move forward and create another region of compressed air. So these regions of compressed air are going to get squished apart. So it's going to be like it's a higher frequency. So therefore, it makes sense that this detector will perceive the sound at a higher frequency compared to the frequency perceived. So that makes sense. So therefore, we know this velocity of the source of sound should increase the frequency perceived. So how does this velocity of the source of sound increase the frequency? How can we do that? Do we plus or minus? Well, again, just using a little bit of logic, we know it would have to be minus. Because if it's minus, that decreases this denominator. And if we decrease the denominator, we increase this fraction, which will increase the frequency perceived by the detector. So now we know, just using a little bit of logic, this has to be positive and this needs to be negative. And again, these will both increase the frequency perceived by this detector. Both the velocity of this detector moving towards sound and the velocity of the source of sound moving towards the detector, both of these are going to increase the frequency perceived by the detector. So again, using some math, that's how we do that. So that's going to be how we set up this equation. So now just solving, we get a value of 350 hertz. So that's going to be the frequency perceived by this detector, which makes sense. That's a frequency relatively higher than the frequency produced. For this last example, I recommend you try to figure it out on your own, because that's the way you learn physics, doing practice problems by yourself. So again, let's say we have the source of sound moving at 50 meters per second away from this detector. Let's say it produces sound at a frequency of 2000 hertz. Let's say the sound travels at 343 meters per second. And let's say the detector is moving towards the sound at a velocity of 150 meters per second. Under these conditions, what's going to be the frequency perceived by this detector? So again, I recommend you sit down, pause the video, and try to figure it out. So if you try this example, you'll plug in the frequency of sound, you'll plug in the velocity of sound, you'll plug in the detector velocity, and you'll plug in the source of sound velocity. And if you do that, you get this equation. But now you have to determine whether it's plus or minus for this numerator and denominator. And if you sit down and really think about it, you should get positive for this numerator. And the reason why is because we know if this detector is moving towards the sound, that should increase the frequency perceived. So how do we increase the frequency perceived with this detector velocity? Well, we have to add it. If we add it, this numerator increases, increasing this fraction, which will increase the frequency perceived. But what about the velocity of the source of sound? Well, if it's moving away, that should decrease the frequency perceived by this detector. So how do we take the velocity of the source of sound to decrease the frequency? Well, we have to add it, because if we add it, that increases the denominator, which will decrease this fraction, which will decrease and play a role in decreasing the frequency perceived. So again, you just plug in the variables, and if you think about it, you'll realize this is positive and this is positive. So then just do the math and you get an answer of 2,254.5 hertz as the frequency perceived by this detector. So again, that's the Doppler effect, and this is the Doppler equation. And again, these are the variables you need to be aware of to determine the frequency perceived by this detector. And also you may get an example where you're given the frequency perceived by the detector. And maybe you're given all these variables, so you have to determine the frequency that was produced by the source of sound. So again, there are lots of different ways you can get asked a question on the Doppler effect. So I recommend maybe just taking a screenshot, and these are all the different permutations, whether the source of sound is moving towards the detector and the detector is moving towards the source of sound. Under those conditions, you set up the Doppler equation like this with plus and minus. And also maybe if they're both moving away from each other, you set up the Doppler equation minus plus. So these are all the different permutations. So really I recommend just looking at this image and thinking about it and seeing if you got the right answer.